Welcome, everyone. This is Laura Podolsky with the National Center for Sustainable Transportation. We're excited that you're joining us today for our webinar, Reducing Greenhouse Gas Emissions Through Intelligent Transportation System Solutions. This webinar is brought to you by the National Center for Sustainable Transportation, the Institute of Transportation Studies at UC Davis, and the Center for Environmental Research and Technology at UC Riverside. Before we begin, I'd like to provide a quick introduction to the National Center for Sustainable Transportation. The National Center is one of 5 national centers designated by U.S. Department of Transportation as part of their University Transportation Centers program. Our mission is to advance a more sustainable transportation system through cutting-edge research, direct policy engagement, and education of our future leaders. Our consortium is being led by the Institute of Transportation Studies at UC Davis in partnership with UC Riverside, University of Southern California, CSU Long Beach, University of Vermont, and Georgia Tech. Today's webinar is a part of a rollout of new research from the National Center, co-authored by our speaker, Matthew Barth at UC Riverside. The final report, along with the one-page policy brief, is posted on our webpage and can also be found by using the link provided in the chat box. We will also be sending a link to the paper and the policy brief in the follow-up email after this webinar. For our time today, we are going to be spending the first half hearing from Matt Barth, with the second half dedicated to discussion with our special guest respondents and Q&A with all of you. So I hope everyone came with questions. We are particularly interested in hearing from all of you regarding research and our knowledge gaps on this issue and what you feel are important research directions on this topic. So please feel free to share those with us either in the chat box, and you'll also have an opportunity to provide feedback to us via the follow-up survey that we'll be sending in a follow-up email. As you can probably tell, everyone is on mute. This is to help us cut down on disruptive noises. So if you hear any dogs barking in the background, that is totally on us. And we do encourage questions, though. So if you do have a question for our speaker or one of our guest respondents, then you can type that into the chat box, again, located in the lower left hand of your screen. You can also use this chat box to let us know if you're running into any technical issues, and we'll try our best to help you. Finally, we will be recording this webinar and post it on our event page for later viewing. Links to where you can find that webinar recording will also be included in that follow-up email, so keep your eyes out. Now, without further ado, I'm very pleased to introduce our speaker and our distinguished special guest respondent for today. Matthew Barth is the Yeager Family's Professor at the Bournes College of Engineering at UC Riverside, and he also serves as the Director for the Center for Environmental Research and Technology. His current research interests include Intelligent Transportation Systems, ITS, and Transportation and Emission Modeling, Vehicle Activity Analysis, Advanced Navigation Techniques, Electric Vehicle Technology, and Advanced Sensing Control. We also have 2 very special guest respondents today. Our first is Marco Anderson, who is a Senior Regional Planner with the Southern California Association of Governments and a contributor to the CAR in 2035, Mobility Planning for the Near Future. He currently works in the Sustainability Department at the Southern California Association of Governments, or SCAG, where he integrates land use and transportation policy. Mr. Anderson is the Project Manager for Mobility Innovation Strategies, the SCAG Electric Vehicle Program, and the SoCal Clean Cities Coalition Coordinator, and the lead for the Sustainability Planning Grant Program. Our second guest respondent that we're very excited to be joining us today is Samer Rajab. He is an IPS Research Engineer at Honda R&D Americas Incorporated. He joined Honda in 2014 with focus on vehicle-to-device safety and mobility applications research. He also serves as Honda Technical Lead in the Crash Avoidance Metrics Partnership, or CAMP, Vehicle to Infrastructure Consortium. His research interests include a mix of intelligent transportation systems and wireless communications comprising vehicle-to-vehicle, vehicle-to-infrastructure, vehicle-to-device, and cooperative adaptive cruise control. So without further ado, I would like to turn it over to Matthew Barth.
Great. Thanks very much, Laura, and I promise I don't have any barking dogs in the background. So thank you, and again, we want to talk a little bit about some of the research we've been doing over the last several years, and a lot of it culminated with this white paper that we wrote as part of the National Center for Sustainable Transportation. I'll first talk a little bit about some general things about energy and emissions and how that's related to traffic and traffic congestion, and then sort of dig into some of the ITS techniques about how that can be addressed. And then of course a major part of what's going on in ITS right now deals with connected and automation, so I'll touch on those issues as well. Of course, we've been concerned about pollutant emissions for quite some time, and we look at things such as criteria pollutants, things such as carbon monoxide, hydrocarbons, NOx, and particles. And really that's been addressed now under the Clean Air Act, and we're slowly making progress there in terms of getting attainment in a large number of areas across the United States. But even still, there are still some criteria pollutant issues that are being dealt with, and certainly transportation plays a major role. But maybe more so now we're looking at greenhouse gases, and of course we want to minimize greenhouse gases that come from transportation. If you look at a lot of the different pie charts, you often see that transportation does account for roughly a third of the CO2 emissions in the United States, and then of that third, roughly 80% of that is surface transportation from cars and from trucks. And the other key thing is, energy and greenhouse gas emissions are pretty closely tied together. So by reducing CO2, you're also improving fuel economy, and vice versa. If you're improving fuel economy, then your CO2 is also going down. So, I often like to say there's 4 general ways of how you can minimize emission impacts from transportation. And we're already doing a lot of this, right? So we're building cleaner, more efficient vehicles. If you look at the progression of the fuel economy of vehicles in general, it's constantly improving. And that's coming through, lighter materials, better powertrain efficiency, new powertrains in electric vehicles, hybrids, fuel cell vehicles. So we are making slow, steady progress there, and because of that, fuel economy is improving and greenhouse gas emissions are going down because we're using more efficient vehicles. Another way to address it is look at the fuels part, right? So using fuels that are less carbon intensive, and so looking at things such as ethanol and biodiesel, those are certainly other ways of reducing the CO2 component. Another, of course, big part would be to look at innovative ways of reducing vehicle miles traveled, or VMT. And that comes into longer term solutions such as land use and better transportation planning, and somewhat to travel demand management. But really the topic of what we're touching on today is really how can we improve transportation system efficiency. And a lot of times this gets kind of lost. I mean, we don't realize how inefficient our transportation system can be unless we're stuck in congestion. We're saying this doesn't make sense. And so really by putting into place different ITS applications and related connected and automation, there are a number of different avenues of reducing CO2 as well as the pollutant emissions as well. And so really that's the topic of the white paper, more or less giving a survey or a general view of what's being done now and trying to quantify a little bit better in terms of what kind of reductions we could expect from implementing these different ITS techniques. One thing that we always look at when we create these emission inventories is, you look at a number of different things. You look, of course, at the fleet themselves, right? The different types of vehicles that we use to get around and move people and goods. We look at what type of activities are they doing. Are they doing a lot of work trips? Are they doing a lot of highway driving versus arterial driving? And all that has to be pretty well quantified. And then lastly, what are the actual emissions that come out of the tailpipe? And that has to be measured as well. So if you put all those together, that's how you come up and quantify what is the total emissions inventory from a particular amount of traffic. And one thing we do to model this, there's a lot of ways, all the way from these larger macro scale models to detailed micro scale models that model individual vehicles. But a common thing that's done is looking at the relationship between energy and emissions as a function of, say, a traffic parameter such as average traffic speed. And I think a lot of people might have seen these type of curves before. If you look at, for example, CO2 emissions in terms of grams per mile, you get high levels at the far left end simply because you're not moving very quickly, you're spending more time on that length of road. It comes down and minimizes somewhere around 40, 45 miles an hour, then starts to go back up, and that's mainly because of aerodynamic forces and things like that. So the graph that we're looking at here is, real-world data where you can measure individual trips, and every point on that graph corresponds to a trip for a lot of data. And then if you do a line fit to the data, you sort of get those typical curves that are used for mainly looking at what is the relationship for something like average traffic speed. Then if you now look at what can we do from an ITS perspective, this is a somewhat complicated slide, but it's again the same curves that we look at. The blue parabolic line there indicates sort of the typical average emissions as a function of speed for traffic. Again, high on the left end and then tailing up on the right end as well. The dashed red line in this case is what's the minimum of what you could do. So if you were traveling at that speed, perfectly steady state, that's going to be your minimum emissions for that particular point. And so the reason we highlight those two things is, we'd like to categorize what you can do to reduce from ITS. You can do congestion mitigation strategies. These things include ramp metering, signal synchronization, better incident management, and really that's taking things from these congested states and hopefully driving it to where traffic moves a little bit faster through the traffic stream, and because of that you get a net CO2 benefit in this case. On the other tail end on the right side, if you want to reduce emissions, you can do things such as intelligent speed adaptation, different things where you adjust the high-end speeds so that they're not as impactful as they would be in typical driving. And so there are different speed management techniques that can be employed. But maybe the larger thing there is what's shown there towards the bottom, which is the smoothing effect. So we're all familiar in congestion, the sort of stop-and-go activity. If you tend to smooth things out, that goes a long ways, and that's kind of taking it from that blue line fit to these more minimal values of what would correspond to traffic moving perfectly at steady state all the way through. And so there are smoothing techniques, and as I mentioned, a lot of the ITS applications do this. The variable speed limits, things like eco approach and departure, which we'll talk about more in a little bit, speed adaptation and things like that. So what this provides is a way of quantifying. If you simply take the average speed as a factor, you can quantify that way. And then if you want to get more detailed, you can look at acceleration rates and things like that to get even more precise answers. But this is a general methodology that a lot of people tend to use. Okay, if you look at ITS research areas, we always like to look at it maybe from a vehicle perspective, a system perspective, and then a human behavior or driving perspective. And there's different parts of ITS that correspond to these areas. One is advanced vehicle control and safety systems. These are the things that we hear about on a lot of the television commercials and all that about adaptive cruise control, crash avoidance systems, longitudinal lane keeping, all these type of things. Then on the system side, it's more your traffic management systems, right? So that's monitoring traffic through sensor systems and then detecting things like incidents and congestion and then doing something to mitigate it, which may be, maybe ramp metering. It may include incident management, different things like that. So there's a number of applications that fall under that systems category. And then lastly, it's driving behavior. And we look at advanced transportation information systems. So this could be things like better navigation, smart parking, different things that can help the actual traveler or the drivers conduct their trips more efficiently. And so when we look at energy and emissions, we often see a lot of these ITS things seem pretty naturally beneficial for reducing energy consumption and reducing emissions. And a lot of we do ITS for several reasons. We do it for safety. We do it for mobility. And when we create ITS that's targeted at safety and mobility, we often get this energy and emissions benefit as well. We refer to those, at least in the white paper, as indirect effects. But the other interesting thing is that in the last 5 years or so, there's been more and more of these ITS programs that are targeted at directly reducing energy and emissions. And we'll talk about trade-offs towards the end of the talk in terms of safety, mobility, and energy. So in the white paper, we give a lot of different examples of, for example, the advanced vehicle control and safety systems, the longitudinal lateral collision avoidance, intersection collision avoidance, adaptive cruise control, all these things that are happening. And these are steps on the way to full automation. It's really things that are happening on the vehicle end. And so simply by eliminating accidents, eliminating congestion, those are things we can quantify, and there's certainly a significant benefit there. On the system side, I already mentioned the traffic monitoring and management, better corridor management. Demand management is certainly an important one there. Again, a lot of it goes to reducing or eliminating congestion and having more efficient operations. And then driver behavior, mentioned route guidance already, providing more information about connectivity to transit and maybe encouraging travelers to shift more towards the transit side. And then simple things such as electronic payment services, variable pricing. A lot of those things are targeted at the travelers and how they can potentially change their trips, and through that, reduce their driving, get better efficiencies, and in turn, getting lower energy consumption and lower emissions. So as I already mentioned, there already are several or many safety ITS programs, several mobility ITS programs, and from that we get these indirect environmental benefits. But just as I mentioned, the last 5 or 6 years, there's been a big push to really develop these environmental ITS programs, and I'll give some examples of that. At least within the U.S., the U.S. Department of Transportation supports several of these programs. There's been several federal highway exploratory advanced research programs that have supported some of these environmental ITS ideas. Certainly it appears in several UTC centers, including our National Center for Sustainable Transportation. And then we're seeing it more and more prevalent in our connected and automated vehicle applications. So connected vehicles in itself is a major part of ITS, right? It's the whole concept of communicating vehicle to vehicle or vehicle to infrastructure, or even extending it to vehicle to X to have a lot of type of communication going on. But again, the idea is usually focused on what can we do, or what applications improve safety, what can we do to improve mobility, and then what are the environmental applications. This slide here shows an early list of some of the connected vehicle applications. This is from the Connected Vehicle Reference Implementation Architecture, where it designates, what are the safety applications and what are the environmental focused connected vehicle applications and mobility. And so a lot of these are defined. If you're interested in digging more, you can go to that CVRIA website and see some of the concepts, how it works, and what the potential is for these. But one of the major things that we participated in was the U.S. Department of Transportation ARIS program. ARIS stands for the Applications for the Environment Real-Time Information Synthesis. But this was really trying to come up with these concepts of what type of connected vehicle and ITS programs can we specifically put into place that is targeted at reducing energy consumption and reducing emissions. So there was a lot of applications. A lot of them are listed here. Many of these have to do with traffic signals. So when you go down an arterial corridor and you encounter traffic lights, There's several applications that were studied in great detail. One of the key ones that we'll talk a little bit more about here is this eco approach and departure at intersections. So I'll give details on that in just a moment. But it's also optimizing the signal timing, again, for energy and emission reasons, and there are some synergies with throughput, traffic signal priority, connected eco-driving. All these things, again, tie into the traffic lights. Then on the other side, there's applications dealing with maybe more on the highway lanes or freeway lanes, things like eco-speed harmonization, cooperative adaptive cruise control. All these were studied in depth in terms of seeing what could they potentially do for the energy and emissions benefit. And then others, you can see the eco-traveler and eco-integrated corridor management. So again, there's the IPS program has a very good website. So if you wanted to dig into more details about these applications specifically, that exist, and it's outlined also in the white paper. So let me just highlight a few, again, simply because we did quite a bit of studies both in simulation and in real-world demonstrations and testing. So this eco approach and departure is fairly straightforward. It's just simply sending signal phase and timing information from the traffic light to the cars. And what that allows the cars to do is to listen and anticipate what the phase changes are going to be, and potentially changing the speed of the vehicle, either to get through the light under a green condition, or maybe slowing down if they know they're going to have to come to a stop anyway, or even safely speeding up a little bit to where you can get through the intersection on the green. And so this is the general diagram of how that works. If you look at a speed versus distance diagram, it kind of outlines the 4 different scenarios. Kind of what I just mentioned. You can, if you're cruising at the right speed and you're going to make it through the green, you don't have to do anything in terms of changing your speed. So that's the scenario 1. Another scenario might be to safely speed up a little bit so that you can make it through on green. Another one is where there's no way you are going to be able to get through. You are going to have to stop, so maybe you want to slow down sooner. And then that last scenario is it might be where you slow down a little bit, stay at a lower speed, get through the green light, and then move forward from there. So it's really just planning a better trajectory for the vehicle as you approach the intersection, and then when you depart, it's getting back up to the traffic flow speed. So there's a lot of variables to this. The signal timing scheme, whether it's actuated versus fixed time. You can plan for single intersections versus multiple intersections. This depends a lot on how well it functions based on congestion level. As you can imagine, if things are very, very congested, this application isn't going to do much for you simply because there's not a lot of room to speed up or slow down. And then another middle point there is, even if you have a small percentage of vehicles that have this capability, you still get a pretty significant level for all traffic. And so we documented cases where just a smaller percent, maybe a 20% penetration rate, can lead to actually a slightly greater benefit simply because cars following other cars that have the technology are also kind of moving at the same traffic flow and getting the benefit. Automation is an issue, whether you want to do this through a driver-vehicle interface versus some kind of automated techniques, and both types of experimentation have been done through different field studies. So the key upshot of this is that, even with all those different variables, the typical answer is, by doing this, you get a 10 to 15% fuel reduction benefit, and that's on an individual vehicle level. But then depending on the penetration rate, then that's all of the traffic that's getting that type of benefit. So as I already mentioned, with heavy congestion, it doesn't perform as well. So usually light to medium levels of congestion is where it's pretty effective. And there's been several tests of this. Some have been at the Federal Highway Turner Fairbanks Research Center. And there's also been some testing in California on El Camino Real up in the Palo Alto area. One project that recently took place is the Glide Path project. Glide Path was doing this eco approach and departure, but using a partially automated vehicle. So rather than telling a driver, this is the speed you want to go at, it basically, like a adaptive cruise control, adjusted the speed of the vehicle automatically, and doing that in a way that it was safe, and if the driver wanted to take that out of the automation, he could take over the car at any time. The results from this test was pretty significant, where if you compare an automated eco approach and departure, that was roughly 20% more beneficial than compared to just manually driving through intersections. And then if you look at using a human driver interface versus manual driving, that was only, say, a 5% improvement. So we think automation has a pretty big role here, even this partial automation. This has been explored also looking at actuated signalization. This one particular test on El Camino Real, El Camino is fairly congested most of the time, so you can see that those results weren't too impactful, roughly 2 to 5%, again, simply because it's difficult to do the speed up and slow down when you already have these levels of congestion. And then I'll go through very quickly on some of the other example ones. Eco traffic signal timing. This is again tuning it, not necessarily just for mobility and throughput, but looking at specific energy minimization. And when you do that, we found a 5% energy benefit. If you look at traffic signal priority, and this isn't necessarily just transit, but you could do freight signal priority. So by doing that, you can get, again, in the range 4 to 6% energy and emissions benefit by implementing these signal priority schemes. Speed harmonization. This is where, if you provide vehicles speed advice on, say, our freeways, and do that in a way where it's anticipatory, where you can get vehicles to mitigate the shock waves, really you can get some interesting results there. On a lot of the simulation work we did was right around 5%. And then you can extend that even further with cooperative adaptive cruise control, which has pretty significant benefits depending on the number of vehicles that have this technology. This is one where we saw sometimes 20, 30, even 40% benefit depending on how you implement this CACC. Okay. So, in summary, if you look at all these ARIS applications, these are kind of the general results of what we've just talked about. And again, there is some continuing work in these different applications. It's really, coming up to where we can document what is the potential benefits. And then we already mentioned, this whole idea of connected vehicles and then pulling in these automation steps. And, the key point I wanted to make here is if you just simply do autonomous vehicles, you might not get the great environmental benefits that you would expect. But when you start to pull in the connectivity, so you have connected automated vehicles, that's really where the potential is in terms of getting the energy and emissions reductions that you want to get. So again, when we look at things such as the Glide Path project, that was a very good example of why partial automation, along with that connectivity, getting the traffic signal information, pays off together in a nice connected automated vehicle experiment. Maybe towards the last point I'd like to make, and also it's touched on in the white paper, is it's not just going to be a vehicle and a systems perspective. It might turn out also to be an infrastructure issue. We're familiar with all sorts of different intersection management systems, all the way from stop signs to traffic lights. There's been a lot of demos that show if you have communication, then you can get away potentially with an intersection without any traffic lights, as long as everyone's communicating and speeding up and slowing down so they don't crash into each other. So that's been demonstrated. But those systems are very fragile, right? If you have one or two vehicles that don't have that technology, it tends to break down and have some issues. But when we say, we have these intersections and designs already, as we progress with more connectivity and more automation, maybe these type of intersections don't make sense anymore, and maybe things like roundabouts make more sense. And so part of what's been studied too is, if you look at these intersection designs, roundabouts have a lot of potential advantages and some disadvantages as well. So one thing is, when human drivers enter into a roundabout, there's a certain point that, the total volume slows down simply because humans don't necessarily merge well together. I mean, they perform the merge events, but they slow down quite a bit to do that. And so you have these potential of, if you could help automate these merging and lateral maneuvers, you could potentially get a lot better performance in terms of throughput with roundabouts. They're also a lot safer. If you look at conflict points, whether they're crossing conflicts versus diverging versus converging merge points, there's a lot of these within a four-way typical intersection, whereas with roundabouts there's a lot less. And so, there's a big safety benefit there. Again, emphasizing the reducing the number of potential conflict points, especially if you were considering this full automated intersection without any traffic lights. So maybe just one point I wanted to make here with the graphs is just simply, if you look at a typical roundabout, and I know it's pretty small text, but this is travel time here, so this is mobility. And as you increase the volume, you can see that, at some point roundabouts start to slow everything down at these relatively medium to low volumes. And again, that's because of the merging effects. Whereas this red line indicates something more of what a typical four-way traffic light would do. So you get better mobility performance as you increase the volume. But then if you introduce things like partially automated merging and things like that, you can still do well with the roundabouts. And that's what these simulation studies told us, is that you can push that volume quite a bit out, as long as you're now involving that connectivity and automation that would allow a roundabout to perform a lot better. All right. So maybe just to summarize at this point, there's always been these three general goals of ITS that focus on safety, mobility, and energy. And I guess one of the takeaways is that there really has been the last 5 or 6 years a concerted effort to specifically target energy consumption and emissions. And we talked about the U.S. ARIS program, but also in the white paper we referenced the Japan Energy ITS program as an example, and the European Union has a number of programs, including EcoMove. And then if you can evaluate each one of these and see these 5 to 10 to 15% benefits, and some of them may be multiplicative. You can introduce a lot of applications and potentially add them up. There's going to be some overlap, but we think there can be a lot of potential if you implement several at once. A question that we get a lot is, if you are improving flow and things like that, are you going to potentially induce demand, which has, of course, a negative energy and emissions effect? And so that's something that's being studied as well. And at least in the white paper, we haven't put too many results in there, but that's certainly a concern. Mentioned before, with ITS, we're often juggling these safety, mobility, and environmental things. And, thankfully, there's a lot of applications that are co-beneficial, right? So if you do things such as a safety application that reduces the number of collisions, that's good for mobility, that's good for safety, and it's good for the environment. But then there could be some potential things where if you want to make things really safe, increase spacings between vehicles, that of course is a net negative for mobility. And so one thing that we're doing as another white paper within the NCST is looking at these different trade-offs between safety, mobility, and energy, and seeing which ones are co-beneficial and which ones truly are trade-off scenarios. And so that's a white paper we expect to see later this summer. And then lastly, with the automation, just to make the point, if we are going to just do autonomous vehicles where the vehicles simply have their own sensors and get around autonomously without doing much communication, there might not be as significant mobility and environmental benefits there. But if you introduce that connectivity, then we think there can be some very good benefits from that type of ITS technology. And then, of course, back to the induced demand. When you introduce a lot of this automation, I think it's clear to a lot of people that there is the very high potential for increasing the amount of travel demand. So that's something that has to be studied and potentially mitigated. So I think that's the end of the presentation. And again, I refer you to the white paper, and if you have specific questions about some of those applications, I can point you to some of the other websites and papers that address that. So Laura, I'll go ahead and finish there, and we can have Samer and Marco talk.
Great, thank you so much, Matt. That was a great presentation. So I am going to put Marco Anderson on the spot first to provide some of his thoughts and reaction in working at a regional transportation planning agency. So Marco?
Sounds great. Thank you, Laura. Can you hear me?
Yep, loud and clear.
Okay, great. So, lately I've been talking a lot about automation and ITS to different audiences. So I have to preface this by saying that in some audiences, I'm very optimistic and really look forward to a lot of the benefits. In other audiences, I have to put my skeptic hat on and talk about some of the challenges. So just wanted to make sure that if I say some skeptical things here, talking to other people who don't believe that this is going to work or that this is a waste of money, I'm very, very pro-investment. So I think there's, from the public sector side, there's a few different responses. And what's interesting to me is that over the last 10 years, especially in California, we are really trying to implement a system where we are trying to get using policy to get public benefit out of a number of private market decisions. And so we see that in the plug-in electric vehicle arena. We see that in kind of how we're approaching ride sourcing and shared mobility. I mean, these are predominantly public sector initiatives, private sector initiatives that we are looking at the benefits and then also trying to be aware of any sort of disbenefits or negative externalities that may come about. And specifically when it comes to kind of these ITS solutions that we're talking about here, I think there's a number of challenges. And one is that traditionally ITS has been approached as kind of an engineering focus, very much a public sector heavy systems approach of introducing hardware into systems, into the lighting systems at a jurisdictional level to achieve really primarily the mobility benefits. And what we're looking at now is kind of a shift between a hardware engineering focus to a software engineering focus and to much more private public involvement. And I think that's going to pose a big challenge. I was at an ITE event, and someone from a private sector company like Qualcomm or something like that was saying, well, maybe the public sector is going to have to change their models of how they operate their equipment. For example, I heard this statistic early last week that in California there are about 45,000 intersections, and Caltrans has jurisdiction over 6,000 of those, and the city of LA alone has 4,700 intersections. And so how do you go about retrofitting 4,700 intersections to achieve some of these goals? And someone said, well, maybe cities should look at kind of leasing model. And I could see the public sector engineers in the city were just shaking their heads saying there is no way on earth that we're going to lease a critical piece of civic infrastructure like our traffic signals or our signal system. And so we really have to kind of figure out how do we get these benefits when the individual costs may be coming down, but when you multiply it over 4,700 intersections, how are we going to get there? So I know the city of LA is actively looking at upgrading ATSAC, and they're starting to plan for that. And so these conversations are happening all over the state. So I think the other thing that's interesting is when we talk about the public sector goals, they also occur at different levels. I mean, clearly safety clearly mobility is very much a jurisdictional as well as an MPO or Metropolitan Planning Organization role. Safety is very much a jurisdictional role. Individual cities are now signing on to Vision Zero. They individually monitor kind of their safety statistics. Energy is a little bit more nebulous, and so that is an MPO state goal when you look at GHG reduction specifically. So there's different parties that need to be involved with the implementation. There's also, again, the need for real public-private partnerships to get this stuff on the ground. I think the other big challenge here is as we talk about the transition to automated and connected vehicles at the federal level, really the NHTSA, National Highway Traffic Safety Agency or Authority, they really talk to the automakers about the individual vehicles. And so they're really talking with them about mandates for automated and connected features on individual cars, specifically with kind of the safety benefits in mind. The automakers themselves would really kind of, left to their own devices, they would be strictly interested in kind of the user experience of automation. Whereas the public transportation sector, MPOs and state DOTs, they really deal with the Federal Department of Transportation and with Federal Highways Administration. So you have two different federal agencies which are actually, I've heard, are really only starting to talk to each other about some of these goals. And so the good news to announce on that front is I was at a Clean Cities conference last week, and the Department of Energy and the Department of Transportation have signed an MOU to really start looking at whole systems and holistic urban transportation systems from an energy standpoint. So the DOE, they did some back-of-the-envelope calculations, and there's a lot of concern. The full automation and connected and automated vehicles, the back-of-the-envelope calculations say it could be anywhere from a 60 to 90% reduction to a 200% increase in energy use. Every MPO that has attempted to model this by basically introducing kind of incremental automation in privately owned vehicles, and the way we model that has changed kind of the parameters of how people would view travel, meaning lower the relative cost of travel, shows an increase in VMT. And the state is actually kind of moving more towards VMT and as a proxy for greenhouse gas reduction. So there's talk that the ARB is going to be reducing new targets, and so very much looking at a reduction in VMT because of a number of co-benefits of sustainability, not just GHG reduction. So again, when you combine those two things, that's a huge concern. Ride sourcing, when we've modeled it, there's an assumption that as ride sourcing takes hold, then along with car sharing and transit and bike sharing, that individual vehicle ownership will go down, and that will lead to kind of more multimodal travel and a reduction in VMT. However, there's no guarantee about that, and nobody's really been able to take a hard look at the numbers. The initial estimates show some promising signs about ride sourcing, but as far as just raw VMT, that's going to take a lot more work. And I guess my last point is, when it comes to ITS and regional transportation modeling, in the past, because of that kind of the overall hardware system, what we've basically done is just done kind of an effect in the model where we say, well, ITS is good, it increases throughput, it reduces congestion and improves air quality, and we treat it as kind of this blanket reduction in all of the negative externalities that we're trying to combat. When we get into the kinds of things that Matt is talking about, as you can see, there's a lot of need for micro simulations, for for modeling of individual performance characteristics of different generations of vehicles and different types of drivers and types of driving conditions, and it's going to pose a huge challenge for us to make an accurate picture of this. So if there's anybody from a state or federal agency on the line, we would love to have more modeling funding, and that will be my wrap-up.
Great. Thank you so much, Marco. And now I would like to open it up for Samer to share his perspective from the OEM side, the car manufacturer side. So, Samer?
Thank you, Laura, and thank you, Matt, for the informative presentation. My personal research focus is really V2X safety and mobility. So environmental is a little bit out of scope for me. Having said that, this white paper has been very informative. For instance, it's good to know that transportation sector is responsible for a third of GHG emissions. And some of these ITS technologies that were presented have a great potential to reduce these emissions and fuel consumption. Now, OEMs have interest in ITS, obviously in ITS technologies in general, and specifically in V2X communications. This technology has been researched quite a bit in CAMP, which is a consortium of multiple OEMs, with a focus mainly on, again, on safety and mobility in the past, but more recently we're seeing more focus on energy, especially eco-approach and departure. So I think it's very exciting, the technology itself, and we need more, obviously, more research in the future, and also future investment in infrastructure. And this is my opinion over here, that this investment would help a lot, particularly at a large scale for B2I deployment, will help a lot and are essential to realize some of these benefits. Now, obviously, some of those pilot deployments that are going on right now helps in engaging OEMs and infrastructure folks. It also makes general public aware of the technology and its benefits. But a more larger scale V2I deployment is necessary to push some of these presented applications forward. Now, I personally see two research questions that arise and that are very interesting. The first one is, how effective are some of these applications at low penetration rates for connected vehicles? Because that's what we're going to see in the first few years. The second one is, I mean, such reduction in fuel consumption and emission is positive environmental impact. However, as highlighted in the paper, it can have a negative impact on mobility. I think that needs to be researched further to answer that question, and how we can really balance this effect between mobility and environmental effects. And yeah, thank you.
Great, thank you so much, Samer. And we do have a couple of questions that have come through, so I'll go ahead and ask those. And again, our speaker, Matthew Barth, if you'd like to chime in, or our guest respondents, these are open to all of you. So this first question does have to pertain more to Matthew's presentation, and it's asking how the fuel-saving benefits are quantified. I think this is a broad question, maybe in the projects or pilots that you reviewed, Matthew. Is it computer modeling only, or is data collected directly from the vehicles?
Yeah, so it's definitely both. You know, I think when you come up with these future concepts, you know, a lot of it has to be modeled. You know, pretty sophisticated traffic simulation models where, you know, individual vehicle movements, getting the vehicle dynamics correctly, getting the correct energy models associated with those different vehicles. So, yeah, when you look at these futuristic, say, intersections or traffic movements, that's really one of the key ways of doing it, is to look at individual vehicle movements, estimate on a second-by-second basis their energy and emissions, and then integrate it all together and come up with a total answer. And, of course, comparing that to some baseline to see what your potential savings is. So that being said, there's also, you know, kind of the next step that says, let's take this to a pilot study or a field study, and that's again where a number of vehicles are instrumented. You can look at things such as the onboard diagnostic port that gives you information on the vehicle state, and you can estimate energy and emissions from that. And so that can be recorded, and as I mentioned, you can integrate that together to see what the benefits are. So things like that glide path project, as an example, that was a field study where we're measuring directly from the vehicle. And so it's a combination of both. You know, they both have their advantages, where the traffic simulation gives you everything. You get all the vehicle trajectories, where usually in the field studies, you know, you're just instrumenting maybe a subset of the vehicles.
Great, thank you, Matthew. And here we have another one. Again, I think this is for your presentation, Matthew, is can you address some of the applications or ITS applications for heavy-duty vehicles?
Yeah, that's a very good question. So I didn't mention too much about that, but you know, a lot of the work that took place, at least in the IPS program, was focused on the light-duty fleet. But what we've seen just in the last year or two is really looking at what's the potential for the same type of solutions for heavy-duty vehicles. So I know that here in Southern California, the Port of LA and Port of Long Beach are really looking at truck movements and goods movement, and a lot of these can be directly applied. So, as an example, that eco approach and departure works just as well or maybe even better for trucks. And so a lot of the things that were mentioned can be applied to heavy-duty trucks, and there's probably some specific applications too that are targeted at trucks. An example of that would be freight signal priority. And that's interesting because you're now dealing with a vehicle that has vastly different weights if it's loaded versus unloaded. You have a wide range of vehicle technology, under different emission control systems. So there is quite a bit of what you can do with trucks, and I think we're going to see more and more of that in the next several years.
And this is Marco. I would add that in Southern California, SCAG has a very active goods movement planning department led by Annie Nam, and they've partnered with the ports and with AQMD on a number of projects, a catenary project, but also there is a pilot with Metro, I believe, and AQMD, a number of partners, and Volvo, working on a platooning demonstration. So I believe that partnership is just kicking off, but it's very excited. And there's again, getting back to the public-private challenge, I had a colleague of mine from the book project who was trying to get a pilot project going in the Inland Empire between a large shipper, a city, and the city Department of Transportation to try and scope a pilot project for signal synchronization, because there was clearly a candidate corridor to get to the nearest freeway. And the challenge was they had very productive meetings, but between the city, the shipper, and the technology providers, they'd all get together and say, this sounds like a great idea, so who's funding this? And everyone would kind of look at each other, assuming, of course, the public sector is going to fund this, but they need to see a demonstrable ROI to fund this sort of project.
Great. Thank you, Matthew and Marco. So our next question, I'm going to try to get this one right. So this is a question about the savings around the eco-timing at the intersections, Matthew. So how do we scale savings at the intersection? So for example, up from an average drive cycle when we have urban and then rural drive cycles in the U.S. So I'm not sure if I'm capturing that question right, but I think it's trying to point to that there's various drive cycles, and how does that,
Sure.
How would the approaches vary, I think, with the intersection and using IPS solutions?
Yeah, it's a very good question, and it's a common question of, that's nice, you're doing it at in an intersection level, a single intersection level. How do you do scaling? And so, there's been different approaches to this in terms of how do you model that. We know of work, for example, in Asia, particularly in Tokyo, that said, okay, we have this technology, now let's figure out how it affects driving on a much larger scale. And so, you can look at it as, take your transportation models, and then now you can say, let's say a certain percentage of intersections have this technology. You can start to simply scale by looking at how many intersections themselves have that capability. But then in terms of driving cycles, if you have enough penetration rate of the technology in the intersections, your typical driving cycle of what we have representing today's driving patterns would change, right? You would see smoothing to those driving cycles, and really it's something where if you're going to use the driving cycle method, it's just a matter of coming up with a representative cycle that includes things such as, like eco approach and departure and other techniques. But the scale up is still a research issue in terms of how to quantify it, and then looking at methods of how to deploy it, and then measure what the benefits are as you do that.
Great, thank you. And we do have a SCAG-focused question. So this one, I believe, is to you, Marco, though others can chime in too if you have some knowledge or insight about how our IPS solutions can be helpful and used in the SCAG region, specifically in LA County.
So again, it comes down to, unfortunately, technology also gets implemented along bureaucratic and political lines as well. So So ITS is a function of, ITS planning is a function at SCAG, but it's also primarily a county-driven enterprise. And so LA Metro is responsible for a lot of the county-level ITS planning, and then individual jurisdictions, including the County of Los Angeles and the City of LA, Department of LADOT, they all have their kind of plans and strategies for implementing ITS. So that's kind of the lay of the land. What we do at the regional level is just try and, getting back to the question about scalability, the path that these things sort of take is that the research kind of develops theories and models them, and then hopefully there's funding for some pilot projects to get some real world results. And then eventually a jurisdiction can kind of take this on and say we're going to do an ITS corridor. Right now the flagship ITS corridor is in Palo Alto. It's a Caltrans facility, El Camino Real. And so they have it equipped with lights and sensors and cameras, and they're just kind of using it as a test bed because of all the automated connected vehicle research labs up there. And then eventually we'll be able to see enough of those things. I know another example is the city of Pasadena. SCAG funded a study for them to determine what are the GHG reduction benefits of specific corridor level ITS investments. And hopefully this would prime them to be able to apply for state funding under cap and trade or other type of things and be able to quantify GHG benefits. The number one concern, of course, is induced demand. So I hope that answers the question. It really plays out at a number of different levels, which makes it more challenging, but also you have a lot of different levels at which you can kind of pilot and fund and test these ideas.
Great. Thank you, Marco. And as a closing question, I might pitch this one out since we have just a little bit more time here. So it would be a quick response from each of you, but something I've been interested in is this new term that's being used more and more, smart cities. And so this idea is to bring together the best science and technology solutions to address some of these common issues local governments are facing, including traffic congestion, managing effects of climate change, improving city services, et cetera. So I was curious from each of your perspectives, from the university to the public sector regional planning agency to the vehicle side, the OEM side, how, is this a new movement towards smart cities? Is it changing any of the partnerships? Is it creating new conversations? And what is your vision for the future? So Matthew, I might pitch it to you first, and then Marco and Samer.
Sure. Yeah, no, I think smart cities is definitely part of the bigger picture, right? So I think if you look at all these different things we're doing with transportation, that's more or less one pillar that makes up a smart city, right? And then so you have these other pillars that deal with energy and smart grids and building management and all sorts of other things that come into place. And so the way I would kind of view smart cities and all the efforts is really a question of integration, right? So we are doing these individual things, these pillars already, and so a smart city offers us the ability to integrate these different things together. And so you can get definite benefits by looking at transportation needs, tying it in with the smart grid and all the other components that make up a smart city. So we're definitely going to see more of this in the future, and including the Smart Cities Challenge that the USDOT is sponsoring. Great.
And Marco, your thoughts?
Yeah, I think it is going to be interesting to watch this stuff roll out. A lot of this sometimes is things that a lot of cities are already doing. It's just kind of bringing it more into focus and highlighting it. The city of LA went through retrofitting all of their street lights with LED and with intelligent sensors that allow the system to be maintained much more effectively and also control the lighting on individual streets. But if you asked a resident on that street, hey, did you know that you're on a smart street now? I don't know that they would be able to perceive that difference. The other thing that really made me laugh was at the Clean Cities Conference, one of the coordinators who had worked on a smart city application that was unsuccessful introduced himself as a representative of a city of average intelligence. And so I think there is something to be said about kind of the buzzword aspect of this. But I think it is a really good focus of just trying to get more intelligent infrastructure in place. The last challenge is putting back on my equity planner hat, is we have to be careful and make sure that as smart city technology is introduced, we're always cognizant of kind of built-in biases. Smart technology that makes things more effective is great, but if it's being used to kind of gather data and then make decisions, we have to really be transparent about what are the criteria for those decisions, who is determining what is or isn't efficient use of public resources, because you can get into some really tricky equity water if that's done behind closed doors.
Great. And Samer, you have our final closing statement.
Yes, so I think from an OEM's perspective, those smart city provide a very good opportunities for vehicle side and infrastructure side to be able to work together rather than doing our research on individual basis. We get the chance to talk and integrate our systems together. So I think it's very promising, but we'll have to wait and see how it develops in the future.
Great. Well, thank you to Matthew Barr. Thank you, Marco Anderson. Thank you, Samer Rajab, for joining us today. Really appreciate it. This will conclude our webinar, but please look out in your email for a follow-up email that will include links to the recording. It will include copies of the PowerPoint, and it will include a link to take an evaluation survey. Please take that. Provide us your thoughts on how today's webinar went, and there will also be a question there for you to share your ideas on what future directions or research questions that we should be asking as we move forward in this area. And you can also mark your calendar for our next webinar, which will be next week on Monday, June 6th. That will be 10 to 11 Pacific Daylight Time. And that webinar will be on the equity impacts of fee systems to support zero-emission vehicle sales in California. And we'll also include some information in our follow-up email. So with that, I hope everyone has a great rest of the day, and thank you so much for joining us.